All right, in this problem, we're looking to figure out the probability that among 12 randomly selected cans, at least one has a defect. So this problem says that a company produces aluminum soda cans for Pepsi, and it has discovered that a defect occurs in 1.1% of its soda cans. These defects seem to occur randomly and independently from one another. That's helpful to hear that the defects are independent from one another. It says, what is the probability that among 12 randomly selected cans, at least one has this defect? So we're looking for the probability that at least one, right? So at least one has a defect. And this is, of course, among 12 cans that are selected. Well, we have this nice relationship that we can always use, which is that, if I try to figure out the probability of at least one having a defect, that's difficult because there are lots of ways that can happen. You could have one can out of all 12 have a defect, and that counts as having at least one with a defect. You could also have 2 cans, 3 cans out of 12, 4 cans out of 12, all the way up to the scenario where all of the cans you select have defects, right? Each one of those is its own separate probability. In fact, there are multiple ways you could have, for example, one can with a defect. Could be the first can you select, the second can you select, the third can you select, or the last can, etc. And all those scenarios have to be calculated and then added together to get the final answer. Well, that would take you forever, right? That's a really long time. Instead of doing that, we can just focus on the one scenario of all possible scenarios where this doesn't happen. And what that means is that, listen, the only way we don't get at least one can with a defect is if all 12 of the cans are perfect, right? That they don't have defects. They're all defect free. If all of the cans are defect free, then we haven't achieved this goal of having at least one can with a defect. So basically that covers the whole universe of possible outcomes. Either you have, a defect in at least one of the cans, or none of the cans have a defect. Therefore, if you add those two things together, the probability of at least one plus the probability of none, that has to be equal to 100%, right? And so essentially, if we just subtract this from both sides, we have a formula we can use to solve this problem. I'm going to write 100% as 1. So 1 minus the probability of none. And then, essentially, we have this formula, right? Which says that whenever you want to know the probability of at least one of something occurs, it's going to be 1 minus the probability of none. And so that's the structure we're going to use to solve this. And in order to do this, we just simply have to use that 1 minus probability of none. But we're going to tailor it to this problem. Notice how it says at least one has a defect. Well, we're going to say none have a defect, right? And that's it. So now we can do this complicated calculation by actually just performing this calculation and subtracting that answer from 1. Okay, so let's see. How do you do that part? How do we get the probability that none out of 12 have a defect? Well, let's draw a space per can, right? Now, I'm not really going to do that because that's a lot of work. There are 12 cans, so I'm just going to do like a ... but realize that this is 12 cans, right? 12 cans, right? And what this is the first can, right? And we're saying to ourselves, hey, what's the probability that that first can is what? Well, over here, we see that we want none of the cans to have a defect. So if we want none of the cans to have a defect, then essentially we want the first can to be without defect, right? Without defect. And we're just asking, what's the probability of that? Well, luckily over here, they told us something about that, right? They said that, hey, the probability of a defect is 1.1%. So the probability that an individual can is defective is 1.1%. Therefore, the probability that the can is not defective, I'm going to write not by putting a bar on top. The probability that it's not defective is 100% minus 1.1%, which I think you'll agree is 98.9%, right? Because of course, if you add 1.1% to that, you get back to 100%. So this is the probability that should go here, because that's the probability the can would not have a defect. I'm going to write it as a decimal when we put it into our position here for the probability space. And so that's the probability the first can we select is without defect. Now, since the cans are independent of one another and the defects occur randomly and independently of each other, then we can assume that the second can, right? This is the second can, has the same probability of being defect-free. So we're going to say 0.989 there as well. And then so on and so forth. All the cans will have the same probability of being defect-free. And so essentially we can do 1 minus 0.989 to the 12th power, and this will solve the problem for us. I'll quickly work that out with my calculator so you can see how that's done, but that's the answer, basically. It'll give us a probability once we do the math. All right, so we're going to do 1 minus 0.989 raised to the 12th power. And when we're done with that, we get our solution. To 3 decimal places, or 3 significant digits, it's 0.124. So 0.124. And that's it.